Right, so the lunar interior, as I said, we don't really have a whole lot of direct knowledge of the lunar interior, but the surface density of the moon is comparable to the surface density of the Earth's surface rocks. So we don't think there's a large nickel iron core, but there could be a little bit of a core at the center. We don't even know for sure if it's completely molten or slightly plastic or something, because our seismographic records aren't really complete in that regard. So there's sort of a little bit of conflict about that. But it certainly was completely molten at around 4 billion years ago. It was essentially completely molten. So what you're seeing here is a body that's cooled off a lot over the last 4 billion years, right? It would have been completely molten. Now there's a little bit of a teeny molten core left, but basically it's really solidified. And this is what typically happens to small objects when they cool. The smaller you have an object, the faster it's going to cool. Yes? Sorry. Right, okay, so what's happening is, well, the moon, during our human time period of existing, the moon's been geologically dead. So there's no plate tectonics on the moon, there's no internal faults moving around. It's basically geologically dead. But if you hit the moon hard enough with a large asteroid, ding, it wouldn't sound like that, it would be a huge thud, but that would actually send vibrations down to the moon. And those vibrations, if you had a detector somewhere else on the moon, you could detect the waves as they have passed through. Very much like what we do on the Earth when we detect the P waves and the S waves and all that stuff. And that's basically the main way that we're able to deduce the interior structure. The main difference is that there's a lot less of those waves on the moon than there are on the Earth, because the Earth creates natural waves. It has its own earthquakes. So earthquakes are happening all the time, and you can observe those. But on the moon, since it's geologically dead, you really have only just a handful of these observations that have been made, so that's why our knowledge is kind of limited. But the thing is that on the opposite side from the moonquake, we basically are seeing both P and S waves. Now remember, if you're on the opposite side of an earthquake, you don't see the S waves, because those get absorbed by the molten core. Okay? So the fact that we're seeing P and S waves on the other side of the earthquake indicates that there's either no molten core or a very tiny, maybe partially molten core, something like that. So it's kind of similar to the evidence that we use when we study the Earth, but there's a lot less of it because of the less, the lack of any natural lunar activity. All right, so as far as the interior structure, we have the actual maria, are these basaltic materials very similar to basaltic lava on the Earth that's solidified. The crust is pretty thick. It's actually thicker than Earth's crust. And then we have this lithosphere, which is basically the solid rock, again, solid rocky. Kind of the softest region out here, the asthenosphere, which is able to conduct some waves, and then the core, which may be actually semi-molten. Now, I mentioned in passing before that the moon is quite massive for the mass of the Earth. It's 1/80th of Earth's mass. And that's actually pretty massive for a moon of any terrestrial planet. You might say, well, it's actually the most massive moon of the 3 moons of terrestrial planets. Now, Mercury has no natural moons. Venus has no natural moons. Mars has 2, and Earth has 1, but Mars' 2 moons are much less massive than the Earth's moon. So the Earth's moon is the unique terrestrial moon in the whole solar system. And may well have played a very significant role in the formation of life on Earth by the creation of the tidal cycle. The tidal cycle, combined with electrical activity and heat, and the primordial atmosphere on Earth, may have actually been the initial progenitor of life on Earth. So the moon may have played a very significant role. So where did the moon come from? We have this massive moon. Where, in heaven's name, did this very massive moon come from? Well, the most natural thing probably is just to assume that it formed along with the Earth, from the same spinning blob of matter that the Earth formed from. We think that the Earth actually formed from a spinning cloud of rocky sort of debris and molecular material. But the problem with that theory is that if they were to have both formed from the same swirling cloud, they should have pretty nearly the same composition, and they don't. Because, of course, we see much more iron on the Earth than we do on the Moon. So the fact that they have different compositions kind of rules out this co-formation idea. Now capture. We'll see as we work our way out through the solar system that many moons have been captured by their parent planets. It's happened many times in the case of Jupiter and Saturn and some of the other outer planets. So one might ask, could not the moon have been captured by the Earth? Problem is that 1 to 80 mass ratio. The moon is pretty darn massive for the Earth, and if the Earth had somehow captured the moon, it probably wouldn't have captured it into the beautiful stable circular orbit that we see now. It would have been a very elliptical orbit, almost like a comet type of orbit, because those are the typical orbits that you capture objects into. You don't capture objects into beautiful circular orbits because those don't really connect with the path that the object came from. So we really don't think that capture is very likely. Another possibility is maybe the Earth was spinning so fast that the moon was sort of ripped apart and spun off from the spinning Earth. That's kind of picturesque, and it could work. In other words, you could certainly fling off a big blob of matter from the spinning Earth. The problem is, it would just keep going most likely. It probably wouldn't then settle into an orbit. Because if you have the Earth spinning around fast enough to rip itself in half and have a moon-shaped blob come off, that blob's going to have very high velocity, and it's difficult to have it maintain an orbit. So we don't think any of these three major theories here can explain it, but there is a fourth one, which is actually the collision scenario. And this is significant for us too, because we'll see that this is going to be an ongoing theme of the course. We're going to see a lot of periods of regular patterns of things, and then occasionally on top of regular patterns, we're going to see weird counterexamples that go against the grain of the pattern that we see. And 9 times out of 10, we're going to end up explaining the weird counterexample by a collision. Because collisions can do lots of wonderful things. They can really change the properties and composition of an object. Collisions are always very rare. And so you might think it's a cop-out to talk about collisions because they're so unlikely to happen. But there's two reasons that we generally end up referring to collisions. One is we're talking about vast timescales of billions of years. So even things that are unlikely can have a reasonable chance of happening over that much time. And the other thing is what we call the Sherlock Holmes hypothesis or way of looking at this, which is once you've ruled out the impossible, the only thing left has to be what happened, even if it's unlikely. It doesn't matter. If that's the only explanation, then that's what happened, even if it's unlikely. And that's kind of what's occurring here. So the most plausible explanation for the formation of the moon that we have these days is the collision scenario where we take a Mars-sized object. Now, it wouldn't literally be Mars, by the way. There's no way Mars could have done this and ended up acting in its orbit. So it would be a Mars-sized object, but not Mars itself, making a glancing collision with the Earth and actually kind of commingling with the Earth's material, changing magma fluids and everything, and then spinning around, and a blob could be sheared off in that process. This is different than the rapidly spinning kind of shear off I was talking about before, because what you're doing is you're not getting the energy from the spin of the Earth. You're getting the energy from this impinging interloper from abroad, coming in and depositing all this energy into the Earth, and basically causing a layer to be sheared off. And this process here, computer simulations show this actually can result in the moon with the properties that we have, with the mass ratio that we see, and in the orbit that we see, in a stable orbit. This is an example of a fairly crude early simulation, a bunch of panels from the book, where we actually start up here with this big impact, and we see a plume of material being blasted off here. So the impact is actually from right to left here. And a big plume gets ripped off the Earth there, and then that starts to solidify, and some of the matter is lost, but eventually we end up with this stable little dot being the moon. So this is what we consider now to be the most plausible explanation. Just last year, a modification of this idea started gaining traction. And the modification is that, as a matter of fact, some of this leftover material may have solidified into a secondary moon for a period of time. So there may have been a period of time, maybe as much as a few hundred million years, when there were actually two moons in about the same orbit, kind of following each other, on this beltway going around the Earth. We have a small moon following the larger moon, like a tree is tailgating a semi. I'm trying to give you terms you can understand. That's practical. doubly traffic area. Okay, so in this scenario, we still have a collision between the Earth and a large-sized body, but there's actually two resulting large fragments. And by the way, there's no real reason to think that you only have one fragment forming from this chaotic process of the collision. No reason. I mean, you could have multiple bodies for sure. The idea is we actually had two. Then, the smaller satellite, which is the Prius, tailgating the larger one, the Moon, they're in nearly the same orbit, so we just have a very slow catching up phenomenon, and then what happens is we get a spectacular low-speed collision, where the second small object, the small moon, actually kind of lands on the moon, our moon. It kind of lands on it at low speed. Not a violent collision, but just kind of a dumping of matter onto the moon. And then, what this does is it explains an observation that I was discussing briefly before, which is the fact that we have less Maria on the far side of the moon. Remember? When we looked at the far side of the moon in the 1960s for the first time, what we were astonished and stunned to find was that there's not a lot of Maria on the far side of the moon. The Maria are pretty much on the near side. And so the initial idea was, well, Earth's tidal effect, pulled this magma through weak points in the crust on the Earth side. But if you remember how tidal bulges work, there's a little problem with that logic, because if you look at the Earth has two tidal bulges, right? I mean, if you look at Earth's tides, one of the tidal bulges of water points toward the Earth, one points in the opposite direction. And you have to have both of those tidal bulges, or you don't get two high tides and two low tides every day. So there's always a bulge and a counter bulge. So if there was a counter bulge, then we would have still gotten Maria on the far side, but we don't see them. And in fact, the highlands are seen to be a little higher in elevation on the far side. So the secondary moon landing on our moon actually explains both those phenomena, because it kind of creates a thicker crust on the far side of the moon, which the Maria, the molten material, is not able to punch through that. And instead we have higher highlands on the far side of the moon. So there's, this is something that probably could be further explored if we're ever able to go to the far side of the moon with manned expeditions. We don't tend to think about sending manned expeditions to the far side of the moon, because we want to stay in direct contact with astronauts, and you're not going to do that if they're on the far side of the moon, right? You're not going to be in direct contact because you can't send a radio signal through the moon's body. So that's why we've always tended to send manned missions to the near side of the moon. So it'll be a while before we actually explore the far side, but we can do that using satellites to remain